Hello everyone. In this final project, our team conducted deformation reconstruction of a soft robotic arm using deep neural network. Our teammates are Xinghao Huang, Yongxin Lin, and Yangchang Lin. In the past decade, soft robotics have been widely studied in research. However, most soft robots still use open-loop control, as a more accurate closed-loop control requires a robot to know its complex continuum shape. There are many published shape reconstruction methods. Most of them rely on cameras or finite element models. One of the emerging methods is to use neural networks and strain sensors to predict deformations. So therefore, in this project, we will try to use machine learning to predict soft robot deformation and see if this is a more accessible method.
Our solution is to use stretchable resistive strain sensor to provide strain measurements for the neural networks. We first build an IVA model of the soft arm and simulate in Abacus. Our input data are strains at sensor located on the model, which will be put into our MLP, and the output are displacements at surface nodes. With the displacement, we can predict the shape of a deformed arm.
We first built an FEA model to simulate various soft robot arm deformation modes while applying different displacement at the free end. For each simulation result, we recorded the strain values at sensors locations. So there are a total of 8 along the y-axis and a total of 4 along the x-axis. We also recorded the 3D displacement values at the edge nodes, which will be used as the training output data. At the end, we generated 2,600 deformations, including bending, twisting, stretching, shearing, and random deforming conditions in Abacus as the training data. And also because there are noises when we conduct the real-world experiment, we calculate the average and standard deviation at the noise and generate Gaussian noises to add to all the training data. Next is to adjust the hyperparameters. We want to know whether fewer sensors have larger loss. So one of them used 12 sensors and other using only the top 4 sensors located close to the fixed space. And you can see our models were able to generate small training loss in long run, but the validation loss remained very high. After adjusting the hyperparameters, the 4-sensor MLP model is underfitting, which means the model may not accurately predict some deformation modes, and both 4-sensor and 12-sensor models have high validation loss. And the trends of training and validation loss show severe overfitting.
The validation result shows that our trained models can actually predict some deformations very well. For example, both MLPs with 4-sensor and 12-sensor inputs can predict stretching, shearing, and mixed bending with low average displacement errors at surface node. Some prediction errors are even lower than 1 millimeter. However, both models fail to predict the direction of pure twisting, which causes extremely large validation loss among all data sets during training. This discrepancy occurred probably because the strains can have similar values when structure is twisting either in clockwise or counterclockwise direction. Thus, the MLP can have a hard time to distinguish between them.
And to realize the performance in real experiment, we have to convert the resistance value read from the sensor to strain. And we obtain the gauge factor through the tensor stretcher experiments. The final result is around 1.22. With this number, we can successfully convert the resistance to strain, and then put them into our MLP to predict the final deformation. In the bending test, the MLP can well predict how the soft arm was bent in the real experiment with input from the 12 sensors. And with 4 sensors, although the overall results did not fit the true deformation well, the MLP still can predict the bending trend near the fixed space. In the twisting test, the MLP still cannot predict the twisting deformation very well with 4 sensors and 12 sensors. With 4 sensors, the predicted deformation of the soft arm does not change at all, and the results predicted with 12 sensors has large volume expansion. Those unexpected deformations are probably due to the hysteresis and drift effects on the sensors. So in the future considerations, we can use strain sensors which have lower hysteresis and drifting issues. The other improvement is to include different sensor orientation combinations on the soft arm. Last but not least, we can optimize the MLP, such as including batch normal and ResNet. Thanks for your listening.